Hello everyone and welcome to my channel. So today's video is going to be a follow-up on the previous video where we derived the equation for finding the coefficients of a multiple linear regression model. So if you haven't seen this video, there will be a link in the description. You don't need to see it, but if you want to see how we derived the equation we're going to use today, check it out. So just to get started, I want to give you a brief reminder of what we did last time. So we derived an equation for our coefficient vector that looked like this. X transpose times x to the minus 1 times x transpose times y. And our model was y is equal to x times our coefficient vector. So here x will be our input matrix, so this will look like this. It's going to be an m by n matrix, so n is the number of coefficients that we're going to use, and m is the number of data points in the training set. So that is x11, x12, x13, all the way up to x1n, and then here we go down to x21, xm1, then here we will be at xmn. And y looks like this, y1, so this will be our outputs, y1 up to ym. So in this video, I'm going to very briefly show you how you can use this equation to develop a very simple linear regression model. And we're going to use a data set from Kaggle. So it's a housing data set containing data on house prices in the US. And you can download it from there. I'm going to put a link in the description as well. Right, let's get started. So I've just opened up a plain Python file. And before we can write any code, we have to import a few modules. So we're going to need NumPy. So we're going to import NumPy as NP. Then we're going to import pyplot from matplotlib, import pyplot as plt. And we're going to import pandas as pd. And then we're going to import seaborn as SNS. So you don't necessarily need seaborn for this, but I'm going to show you a function that is really nice to investigate your data once you open it. So first we need to load the data, and we're going to use pandas to do that. So it's going to be pandas.read_csv, and I called the downloaded file usahousing.csv. And we can have a look at the dataset actually. So there are a few fields in there: average area income, average area house age, the number of rooms, the number of bedrooms, the population of the area, the price, and the address. And what we want to do today is we want to predict the price based on all the other inputs, apart from the address. But before we can do that, it's always useful to actually look at what our data set contains and how the inputs or how the different fields in our data set are related with each other. And there is a really nice function in Seaborn called seaborn.pairplot. And we can just pass it a pandas data frame, and it will work immediately without any issues. Then we have to do plt.show, and then we can run that code in the terminal. Okay, so there would be Python 3. It's going to take a while. But here you can see the pair plots that Seaborn created. So of course you can do this yourself, but this is a very neat shorthand because it would take a very long time to set all of this up. So here we can just see the distribution on the diagonal. We can see the distributions of the individual data set, of the individual rows, and they're basically all normally distributed, apart from the number of bedrooms. And what we are most interested in is the last row, which basically shows us the price against all of the input values that we want to use. And what you can see here is that they're all correlated. So the price increases as the income increases, as the age increases, as the number of rooms increases, and so on. And the second important thing is that if you look at kind of the dependence of, for example, the population on the income, there isn't really a clear dependence. It seems like it's just basically normal distribution. And that's very important, that our inputs are not correlated, because we want them to be independent. Otherwise, they wouldn't really provide additional information. They would just be providing the same information as the other variable. And to visualize that a bit more concisely, we can actually plot a heat map of the correlations between all of the columns in our dataset. And C1 can also do this quite nicely. So instead of plotting a pair plot, we can plot a heat map. So sns.heatmap, and then we just pass it a correlation object, which is data.core. Then we save. I don't know why saving takes so long. It might be one of my plugins that I use for Vim. So if you run it again, we're going to see a heat map. And basically, for those of you who know what correlation is between 1 and -1. 1 meaning that it's perfectly correlated. So if area income increases by 1, area income also increases by 1. So all of the diagonals are, of course, going to be 1. What's very interesting is that all of our everything that we're going to use as inputs, so those are these 5, they are not really correlated at all, apart from the number of bedrooms and the number of rooms. But otherwise, they are very close to 0 in terms of correlation. And that basically tells us that they are independent of each other. And the other important thing, which we've already seen in the pair plot, is that they are all correlated, positively correlated with the price. And that's very good for a linear regression model or for machine learning in general. So that basically tells us that they all provide distinct information, apart from maybe the number of rooms and the number of bedrooms. So you could consider dropping one of those 2 variables if you wish so. But we're not going to worry about that too much. This seems to be good enough for us. So let's get back to Vim and get rid of the heat map. So to start off with, we're going to set up a matrix. I like to work with plain NumPy matrices or NumPy arrays, and not really with pandas data frames, but it's just a preference thing. So we're going to do np.ones, and then we're going to pass it data.shape 0, 6, because we have 5 inputs, and the last row or the last column has to be all 1s, as we've seen in the last video. So by using numpy.ones, we already get 1s in the last row. And then we're going to assign the first few columns. So the first 5 columns of X will be data, and Pandas has a very nice slicing feature. We can just do this, area population. And I think there should be a .lock here. So you can use this to slice this like an array, but you can use the names of the columns essentially, which is very nice. And for Y, this is really annoying. It's so slow. Yeah. All right. So Y is equal to data, and that would be the price. And then we want to split our dataset into a test set and a training set. And so I already know that there are about 5,000 entries in our dataset. So what we can do is ytrain is equal to y to 4,000. So that's going to give us 80% of our data points in the training set. And xtrain is equal to x up to 4,000, and we want all the columns. Then ytest is equal to y everything from 4,000 onwards. The same for xtest, 4,000, and we want all the columns. All right. So now we have to implement our function, a function that calculates our coefficients. So we're going to get 5 coefficients, of course, and we can look at them in a bit as well. But first we need to implement this. So let's get rid of plt.show for now. So we want to define a Python function. We're going to call it train, and it's going to take two inputs, x and y. And it's going to return the coefficients. So just if you look at this equation, these are just matrix products and an inverse. So we're going to need numpy.linearc.inverse, and it's going to be x.transpose at, so that's just matrix multiplication. It's a shorthand for numpy.matmul. It's x, and then we want to multiply that by x.transpose, and then we multiply that again by y. And that should give us effectively our coefficient vector. There is an equal sign missing for those of you who spotted it. So what we want to do is we want to define our coefficient vector as train, x train, comma, y train. And now we can have a actually print C and see if we actually get 5 coefficient vectors. So let's run this. Ah, yeah, there is a typo, of course. Transpose. Okay. Yeah. So we're getting, yeah, it's 6 coefficients actually, because we also have the intercept, which is the last one. So everything is like we expected. And now the next thing we want to do is we actually want to look at how well we're doing on the training set. And of course, you could calculate some sort of error. We're not going to do that. I want to show you a more visual way. So the best way to do this is just to plot a scatter plot. And we want to plot the training values on the x-axis and our x train multiplied by our coefficients, which, if you recall, is the way our model is defined. We want to plot this, and basically, if our model is very good, then everything should be on a straight line along the diagonal of the plot. Let's run this again. And yeah, on the training set, we seem to be doing very well. Of course, there is a bit of scatter because maybe there is some information missing for the model, or there's just some noise on the data set, which we don't account for. All right, so, but what is way more interesting is to actually have a look and see how well we do on the test set, which we didn't use for training. So we're going to use y-test and x-test. And save. I really have, let me do something. CUC uninstall Pyrite. Yeah. Now we don't get linting anymore, but at least it should be faster to save. All right. Looks very similar to our previous plot, but we only have about 1,000 data points now. But so again, on the y-axis, we have our predicted values, and on the x-axis, we have our actual values. And if our result would be perfect, it would be a straight line from this corner to this corner. And that looks fairly good. So we're doing pretty well. There is one more thing that I want to show you, and to kind of get the point across that you can't really have things that are linearly dependent. And I'm going to show you this in a very obvious way. I'm going to use, say I want to set the first or the second column of our input matrix to data at area population. So basically this is going to be the same. And that means they are perfectly correlated. And what we should see is that we have a problem with the numpy.linearc.inverse function, because you can't have things that are linearly dependent when you compute an inverse. And that's exactly what we're seeing. We're getting a singular matrix. So a singular matrix is just a matrix where the determinant is 0, which means you can't compute an inverse for it. And that's what happens when they get strong linear dependencies. And it might not happen immediately if there's some noise, but if you have a very strong linear dependency, and so linear dependency would just be, if that is our X matrix, and we call the first column x1 and the second column x2, then a linear dependency between x1 and x2 would be if x1 is equal to some constant a times x2. That's exactly what we've done. We've basically set two of the columns to be exactly equal, so they are perfectly correlated. And that is very bad for inverting a matrix. So you want to avoid this. So another thing that I want to do is to actually just use the input that is strongest correlated for our model. And that would be 0th column is going to be data and average area income. So if you remember from our previous plot, this is the data point that is, or the column that is strongest correlated with the price. And we should see that the model still gives like reasonable predictions, but because all of the other columns also provide valuable information, it shouldn't be as good as it was previously. And that's exactly what we see. So we still get, we still get like somewhat of a straight line, but it's by far not as good. So yeah, that's what happens if you don't provide enough information for the linear regression model. Anyway, so that's it for today. I hope you got something useful from this video, and if you did, please hit the like button and the subscribe button, and drop a comment below to let me know what else you want to see from this channel. Until then, see you next time.